All right, thank you very much for the introduction. And let me also say thank you to the organizers for inviting me here and offering me the opportunity to speak. I'm particularly excited to be speaking at this conference because Alexis was my thesis advisor. I finished my PhD in Austin in 2019. So it's a good time for a little story about my time as a PhD student. So I started working with Alexis in the spring of 2015, and our first project was an application of the DiGiorgi method to the 3D quasi-geostrophic system. And so we worked pretty hard on that project, and after a year and a half, we wrote our first joint paper together. And sometime shortly after that, Alexis suggested to me a convex integration project. And I guess I was really excited about DiGiorgi and not so excited about convex integration, because I asked him, why should I care about this other method of building solutions to PDEs? It has nothing to do with what I was doing before. And in his characteristic way, he very patiently explained to me that there was good mathematics to be done and that it was an active area with lots of people interested in it. And I also remember that you said that there would be special events and conferences devoted to this topic. And I was lucky enough to participate in one of these events. It was a special year on the H principle at the IAS. And that was actually where I met my collaborators, Shinju and Vikram. She was a postdoc at the IAS at that time. Vikram was a graduate student at Princeton. So there's a direct line from Alexis's guidance to this theorem that I'm about to tell you about today. And so let me say thank you, Alexis, for your mentorship and friendship over the years. All right, so let us begin. So this is a talk about the 3D Euler equations, but for the purpose of motivation, I'll also discuss Navier-Stokes. And I will always pose these equations on the three-dimensional periodic box, so periodic boundary conditions. And of course, Navier-Stokes is the case when the viscosity parameter is positive, and Euler is the case when nu equals 0. And my focus today will be in the case nu equals 0, or at least for the purpose of motivation, the limit as nu approaches 0. And this is the so-called turbulent regime. And so turbulence is something that we can observe in real fluids in the lab or somewhere in the world. And we can also simulate the solutions of these PDEs on a computer and make observations about the simulations. And somewhat remarkably, both at the level of the experiments and the numerics, there's a few properties which we consistently observe, which I'll tell you about. And so it would be good from a mathematical point of view to be able to build solutions to the PDEs which are consistent with these properties. And that's the goal of the so-called Onsager program from my point of view. That is to build solutions to the PDEs consistent with these three facts that I'll tell you about. All right, so that's the story of the Onsager program. And there's no reason to keep you in suspense on what my theorem says. It's fairly simple. So if you consider the 3D Euler equations and you fix a regularity parameter less than 1/3, then I can build a solution, weak solution, which has almost 1/3 of a derivative in this L3-based Bestov space. And this solution, in addition, satisfies the local energy inequality. All right, so my goal today is first to motivate this theorem and tell you a bit about the background. Some of you may know this story quite well, but it's a story that I like to tell, so I'll do it again. And then at the end, I hope to tell you a bit about the proof. All right, so let's start with a little bit of backstory on turbulence, and I'll weave in some of the mathematical results as we go. So here are the Navier-Stokes equations for an incompressible fluid constant density. Upon non-dimensionalization, we see the Reynolds number appearing in front of the Laplacian. And of course, the Euler equations correspond to the case of infinite Reynolds number, and the Navier-Stokes equations, finite Reynolds number. All right, so let's look at some pictures of flows at different Reynolds numbers. So this first picture is at a pretty low Reynolds number, and what's being depicted is flow past the cylinder. So here's the cylinder, and the flow is being forced left to right. And because this is a low Reynolds number, the flow is very predictable, and it enjoys many symmetries. So no turbulence. In order to see turbulence, we should start increasing the Reynolds number. So here's an increase by 1 order of magnitude, roughly speaking. And this is not a picture of turbulence, but it's a very pretty picture nonetheless. So this is a von Karman vortex street. And what's being depicted is flow again past the cylinder on the left here. And in the wake of the cylinder, we see these vortices shedding in an alternating up-down fashion. All right, but in order to see turbulence, we have to keep increasing the Reynolds number. And another order of magnitude gets us basically to the state we want to be in. That is the state of homogeneous isotropic turbulence. So this is flow past a grid. And you see that in the wake of the grid, we have vortices and eddies at a multitude of scales. All right, so I want to focus on 3 aspects of this state of homogeneous isotropic turbulence. And these aspects are the phenomenon of anomalous dissipation, the 4/5 law, and intermittency, because these are the 3 properties which are going to motivate the theorem that I showed you on the second slide. All right, so let's start with anomalous dissipation. So if I write down the Navier-Stokes equations, and I assume that I have a smooth solution, I can take the dot product of the equation with U nu, and I derive, of course, the pointwise energy balance. Now, of course, integrating this in time, I see a few things. First, I see that if nu is equal to 0, then smooth solutions of Euler conserve the energy, whereas if nu is positive, then any dissipation of energy is a consequence of this term here, which of course comes from the Laplacian. All right, but in general, solutions to the Navier-Stokes equations may not be smooth, especially if I'm considering Euler. So let me write down a more general energy balance which holds for weak solutions. So this more general energy balance has to be obtained by mollifying somehow and passing to a limit, because I'm not allowed to test with the solution anymore because it's not smooth. And we see an extra term appearing in this balance, which is called the Duchon-Ribert measure. And this Duchon-Ribert measure has a formula. So it's the limit as a mollification length scale passes to 0 of the gradient of the mollifier. So I pass the derivative onto the mollifier, and then I have an expression which is cubic in the velocity. And that's because, morally speaking, this term is arising from trying to take the dot product of the nonlinear term with U. All right. And the zeroth law of turbulence, or this phenomenon of anomalous dissipation, posits that if I compute the energy dissipation rate and I take some suitable average, and then I take the limit of the viscosity parameter to 0, I get a strictly positive number in the limit. So this says that the energy dissipation in the inviscid limit is coming not just from the Laplacian, but at some point this Duchon-Ribert measure may be contributing as well. All right. So in terms of mathematics, we have a nice class of solutions to the Navier-Stokes equations. These are the suitable solutions of Caffarelli, Cohn, and Nierenberg. And a suitable solution is one which enjoys some regularity criterion and satisfies a sign condition on the Duchon-Ribert measure. And it's not too hard to see that if I take a limit of suitable solutions converging in L3TX to an Euler solution, then the Euler solution inherits this sign condition on the Duchon-Ribert measure. All right, and the second thing to point out about the Duchon-Ribert measure is that I can figure out under what conditions it will vanish. So if we look at the units of this, the mollifier with the gradient on it spits out a 1/length scale, and I have these velocity increments, which are cubic. And if you think about this for a few minutes, you see that in order to make this Duchon-Robert measure vanish, I need each velocity increment to spit out L to the 1/3 in an L3 sense. And what that's saying in terms of regularity is I need my solutions U nu to become unbounded in B alpha L3T B alpha 3 infinity if alpha is bigger than 1/3. So in the inviscid limit, I expect some loss of regularity. And this is the threshold which will allow for anomalous dissipation. All right. So,
Is there any best choice for this test function phi L, your modifier?
Yes. So the expression for D of U nu is independent of the choice of modifier. That's a good question. All right. So the second aspect of turbulence that I want to discuss is Kolmogorov's 4/5 law. And this dates back to his 1941 phenomenological theory of turbulence. And his assumptions were the zeroth law, so non-vanishing energy dissipation rate, and some symmetry assumptions, so translation, rotation, and scaling symmetries for these velocity increments. And as a consequence of these claims and essentially dimensional analysis, Kolmogorov was able to make predictions for these longitudinal structure functions. So I take a velocity increment in the direction z hat. Z has a unit vector of size L. L is a scalar. I take the dot product with z hat, raise it to the p, and take a suitable average. So Kolmogorov predicts that this scales like epsilon times L to the p on 3. All right, so let's translate this into a prediction about regularity. So if I look at this this structure function, this is a velocity increment raised to the power p, and it has some scaling. If I make the jump to a Bessov norm, the right Bessov norm to compare this expression to is the B1/3 p infinity norm. So Kolmogorov style scaling arguments are really saying that solutions remain bounded in B1/3 p infinity for all p. And as I take p to infinity, what that's really saying is that solutions are C1/3 in space for each time. All right, and I just want to point out that I'm writing these rather opaque bracket symbols, but there are at least some results in turbulence which do not require an averaging procedure. So here's an example of one first written down by Eink. So this is a local deterministic version of the 4/5 law, which says that if I average velocity increments dotted into the direction of the increment on the unit sphere, then I take the limit as L goes to 0 with a 1/L in front, I get exactly minus 4/5 times the Duchon-Robert measure. All right, so this is in some sense an exact law for turbulent solutions of these equations. And it corresponds in some sense to B1/3 3 infinity regularity because I'm measuring something which is cubic. So L3 is the Bessov space that I'm comparing this to. All right, so at this point, we should bring up our Onsager. And this is a quote from his famous statistical hydrodynamics paper, which says that basically dissipation could take place in the 3D Euler equations despite the absence of viscosity. And Onsager really put his finger on the culprit of this dissipative effect. He knew it was because the velocity field does not remain differentiable. And as we already sort of pointed out, we can see that phenomenon at the level of the Duchon-Robert measure. We see that this vanishes if U has some regularity. And this was proven by Duchon and Robert. Namely, if U belongs to this Bessov space for alpha greater than 1/3, then the Duchon-Robert measure vanishes. All right, so that's 1/2 of a proof of Onsager's conjecture. And his conjecture was that L infinity T C1/3 X is the threshold for energy dissipation. And the other half came a few years ago, first in the context of non-conservative solutions by Izet, and then in the context of dissipative solutions by Buckmaster, Dwellis, Shekelahidi, and Bacall. All right, so this is a very nice validation of a very old conjecture, but there's a few pieces that I want to add into this story. And the missing pieces are the local energy inequality and this phenomenon of intermittency. So let's start with the local energy inequality. So if I look at the Duchon-Robert measure of the solutions that Izet and Buckmaster et al. Constructed, they don't satisfy the sign condition. And I know that the sign condition is necessary if I want to observe these solutions as a limit of suitable Navier-Stokes solutions. All right, so these solutions cannot arise then as limits of suitable Navier-Stokes solutions. And people have attempted to construct solutions which do satisfy the sign condition, but the best result to date had been in Holder-based spaces, and it was C1/7 minus. This was a result of Camilo Dwellis and my collaborator Hyunju Kwan, and this was following an earlier work of Izet. And there do appear to be some fundamental obstructions to reaching the C1/3 threshold in these constructions. All right, so the last missing piece is this phenomenon of intermittency. And if we look at the Onsager theorem, we see that the conservation of energy requires an L3-based regularity criterion, but the dissipative solutions were constructed in C alpha. And you may ask if this difference between L3 and L infinity-based Besov spaces is merely a mathematical artifact, or is it actually reflective of something that's happening in turbulence? All right, so let me try and convince you that it's actually reflecting this phenomenon of intermittency. So in terms of regularity, Kolmogorov is saying that the regularity exponent is 1/3 in any LP space. But we can make measurements of turbulent flows in experiments and numerics, and we can see we can estimate what the exponent should be as a function of P. And this has been a question that's been under investigation for many decades. And what one generally observes is a particular type of deviation from Kolmogorov scaling. So there's always agreement at the P equals 3 level. That was where the 4/5 law was phrased. That's the exact law. But if P is less than 3, we observe solutions with more than 1/3 of a derivative in LP. And if P is larger than 3, we observe solutions with less than 1/3 of a derivative in LP. And I put some citations here. So actually, Onsager and Kolmogorov themselves were aware of this phenomenon of intermittency. And people are still doing numerics more or less to this day. There's a very interesting paper of Iyer, Srinivasan, and Young, which asserts that the second order structure function exponent, or the WS2 regularity exponent, deviates from Kolmogorov's prediction. All right, so one could take away from this discussion that B1/3 3 infinity seems like a good space for turbulence, but C1/3 is perhaps not. And I'll put L infinity here, partially to draw an analogy with Berger's equation or conservation laws, in which this is exactly the regularity that we see in the inviscid limit as we take the viscosity parameter to 0. And Iyer, Srinivasan, and Young also sort of suggest that solutions don't retain any Holder continuity in the inviscid limit. All right, so let's just draw a picture so that we can try and understand what this intermittency is saying. So if we think about the turbulent cascade, we have some input from forcing at low frequencies or large scales. And the energy cascades down to smaller and smaller scales. But this cascade is not space filling. So if I look at a sort of mother eddy and all of its daughter eddies, the eddies are not filling up the space that each previous generation of eddies filled up. And this is a good way to picture intermittency. It's the sparsity in the behavior of the solution. All right. So
this is not time, right? This is a.
It's not really time. It's as if you drew the collection of eddies at one time, and then you waited a little bit, and you saw how they cascaded down to a collection of smaller eddies and smaller eddies until you had the infinite frequency. But this cascade is occurring continuously in time.
When you say sparsity, do you mean physical space or frequency space?
Say again? Sparse in physical space. Yeah, of course, sparsity in physical space is probably related to a stretching of frequencies in Fourier. All right, so I think it's a good idea to draw a few examples of intermittent functions. So these are functions whose regularity exponent depends on the LP space in which I'm measuring it. So one example is the Cantor function. And perhaps a simpler example is just the Heaviside function or any function with a jump. So this Heaviside function belongs to B1 over P infinity for all P. All right. So this brings us then to the topic of strong Onsager conjectures. So I want to consider not just the Euler equations, but the Euler equations with the local energy balance encoded with the Duchon-Robert measure. And the strong L3 Onsager conjecture says that alpha equals 1/3 is the sharp threshold at which I see two different behaviors. In the case alpha bigger than 1/3, the Duchon-Robert measure vanishes. This was known from the work of Duchon and Robert. And if alpha is less than 1/3, then I should be able to find weak solutions for which the Duchon-Robert measure is positive and the kinetic energy is decreasing. All right, so this is the strong L3 Onsager conjecture. And I should write down at least a stronger conjecture, which is that not only can I construct these Euler solutions with positive Duchon-Robert measure or non-negative, but I can even recover them as a limit of sequence of suitable solutions to Navier-Stokes. So at the moment, this is out of reach, but this is exactly the theorem that we proved with Hyunju and Vikram.
Excuse me, I'm not sure to understand. Do you have any data here?
So you have to be careful about building the initial value problem in this story, because you can't run afoul of weak, strong uniqueness. So I don't treat any smooth initial data and build a dissipative solution. We can treat some initial data. We didn't think too hard about how broad the class of initial data is, but my instinct is that it's a fairly broad class of rough initial data that we can treat. That's a good question. All right, so let me state the theorem that I'm going to discuss, and also its predecessors. So I started working on this type of problem with Tristan Buckmaster, Nader Masmoudi, and Vlad Vikal a few years ago. And the first result that we were able to obtain was that there exist solutions to 3D Euler which are intermittent. So they have a regularity exponent in L2, which deviates in the upward direction from Kolmogorov's prediction of 1/3. But these solutions don't satisfy anything resembling the 4/5 law, and they don't satisfy the local energy inequality, i.e. the sign condition on the Duchon-Robert measure. All right, so the next bit of progress was a joint work with Vlad, in which we were able to build the 4/5 law into this picture, meaning that we had regularity, which was almost at the B1/3 3 infinity threshold, which is consistent with what we know about turbulence. And the final missing piece was the local energy inequality, and this is what I was working on with Hyunju and Vikram. And as it turned out, the first thing we had to do was actually rewrite the proof of my theorem with Vlad using a sort of wavelet-inspired scheme that I'll I'll describe a bit later. All right, but with this new method of proof and a bit of further work, we were able to prove this theorem here, which builds solutions to 3D Euler with decreasing kinetic energy. They belong to almost the critical L3 Besov space, and they're almost bounded. So every time I write minus, I mean that if you give me any exponent less than 1/3, I can build a solution in that Besov space. And similarly, L infinity minus means that my solutions can live in arbitrarily large LP spaces, large P. All right, so this is the theorem. And the basic strategy is to construct this dissipative solution as a limit of approximate solutions. And this limit of approximate solutions should converge in the topology that I want to find my limiting solution in. And these approximate solutions are constructed via an inductive procedure which dates back to Nash iteration. And probably many of you have seen talks about Nash iteration or convex integration before. But I do want to attempt to convince you that there are some ways in which our Nash iteration is rather different from the previous Nash iterations for the Euler equations. All right, so what are the main differences? The first difference is that all the Nash iterations to date for the Euler equations worked directly in L2 or L infinity. And we replaced this L2 or L infinity based framework with an L3 based framework. Of course, adapted to the regularity that we hope to achieve in the limit. All right, the second difference is that the general paradigm for these approximate solutions UQ is that they're obtained by Fourier truncation in space of my limiting solution U. So this is basically choosing a basis and building the solution term by term in that basis. And what we do instead is choose, in essence, not a Fourier basis, so that the UQs are partial Fourier sums, but a sort of partial wavelet basis in which frequency separation has been traded for a mixture of space-time and frequency separation. All right, and the final interesting aspect of our iteration is that the pressure plays a very fundamental role. And what I mean is that, of course, I want to know estimates on my velocity field. And traditionally, this was done by propagating the LP norm of the velocity. But what I actually propagate in this scheme is the LP norm of the pressure. And then every other estimate is made by comparing whatever I want to estimate to the pressure. So how big is it compared to the pressure? And this is rather different from the way that estimates were propagated in Nash iterations to date. All right, so I want to spend the last 20 minutes or so, 25 minutes, talking about this Nash iteration. And of course, the two questions are, how do I set up the induction? And how do I propagate the inductive assumptions to the next stage of the iteration? All right. So in order to warm up to the L3 iteration, let's set up the C alpha iteration, or I guess I call it C beta. So the idea is that I posit the existence of a collection of functions, so a velocity field, a pressure, and a few error terms, which appear inside of divergences on the right-hand side of both the Euler equations, appearing here on the left-hand side, and the local energy inequality appearing here on the left-hand side. And the success of my scheme will mean showing that these right-hand sides converge weakly to zero in the limit as Q goes to infinity, so that I get a solution to Euler which satisfies the local energy inequality. For the time being, I'm not writing a careful formula for this phi q because at the moment it's not important. All right, so where do these equations come from? Well, you can guess the form of the equations by taking a solution of the Euler equations and applying a frequency projector. And if you do so, you basically get a relaxation which looks something like this. So our heuristic here is that UQ is a partial Fourier sum of my limiting solution U onto spatial frequencies. Which spatial frequencies? So I'm going to set a frequency parameter, which I call lambda q. And lambda q is growing slightly super exponentially. So I put the b to the q in the exponent. But in order to maximize the regularity exponent that I find in these iterations, one generally sends b to 1. So the idea is that I want to leave as small a gaps as possible between the frequencies of my successive terms in the series. All right, so I have the equations, and I have heuristic at least for where the equations came from. They came from a Fourier truncation. And now what I need is inductive bounds on the size of these various functions. And I didn't write anything too precise here, but the basic idea is I take a few derivatives, no more than 2 or 3, both spatial derivatives, which I'll denote by dn, and material derivatives along the velocity field uq. And I apply these differential operators to all the various functions appearing in my relaxation, and I posit some sizes in terms of the frequency parameter lambda q. So at the moment, the right-hand side, the specific expression for the right-hand side isn't important. I just posit some bounds. All right, so this is the C beta setup. And now I want to explain a bit this Wavelet-inspired L3 setup. So what's the first thing that changes? The first thing that changes is that I have what we refer to as the intermittent pressure, pi q, appearing inside the relaxation. And I refer to it as a pressure because it appears in this equation inside the divergence of a symmetric tensor. So I can think of minus pi q identity inside of a divergence as a pressure. It's just minus the gradient of pi q. And of course, pi q shows up in here as well, but I don't want to get into the specific form that it appears, so I'll just say that this phi q now depends somehow on the intermittent pressure pi. All right, so the intermittent pressure pi has appeared in the equations. And the next question is, where did these equations come from? So rather than finding these equations by applying a partial Fourier sum, I want to find them by applying a partial wavelet sum. And I guess there was supposed to be a picture here, which I forgot to draw. So I'll draw it on the board. Maybe pick a different piece of chalk. So what's the idea of the partial wavelet sum? Well, if I'm working with the usual Fourier basis, then my oscillations are just sines and cosines. And I have a frequency parameter lambda q. But the basis that I'm going to use doesn't have a set of oscillations which is space filling. It has oscillations which are much sparser and more peaked. And so I need parameters to compare the thickness of these oscillations and the distance between neighboring oscillations. So the thickness I'll refer to as lambda q inverse, and the spacing should be much larger. It's lambda q rq inverse. And for me, rq is less than 1, which ensures that these oscillations are spaced at a greater distance than the thickness of the oscillation itself. All right, so this is somehow the fundamental building block of my wavelet decomposition. And you should then think of UQ as a partial sum in the expansion in these basis functions. All right, and one consequence of expanding the distance between oscillations is that the frequency support has now expanded as well. So the frequency support of this type of function is at the large end, it's lambda q, but it could be as small as lambda q RQ. This is the inverse of the distance between oscillations. And if I smear out the frequency support of a term in this series, then it's not necessarily disjoint in frequency from the neighboring term in the series. All right. So I have this idea that my equations are a partial wavelet decomposition of the limiting solution. And I need to introduce a parameter which describes how much exchange there is between pure frequency separation and mixed frequency and space-time separation. And the parameter that we introduce is, we call it n bar. And the idea is that if I look at terms in the partial sum of my limiting solution, so I call each term in the partial sum WQ prime. So if two W's, Q and Q prime, are close to each other, i.e. they're less than n bar apart in the terms in my series, then their space-time supports are disjoint. And conversely, if I posit that I have terms which are far away from each other, then their frequency support is disjoint. So I do have some type of orthogonality between the different terms in this series, but it's a mixture of frequency separation and space-time support separation. And the other consequence of smearing out the frequencies and making this trade between space-time and frequency support separation is that the right-hand side of my relaxation now becomes a little more complicated. So there's a whole menagerie of terms here, which are all oscillating at different frequencies. And so I have to divide them into bins according to which frequency they oscillate at. All right, so these are our heuristics. And now I need some inductive bounds. And I said that everything was going to be in terms of the intermittent pressure. So the starting point for my inductive bounds is an L3 halves norm on one of these intermittent pressures. So pi qk is one of the terms which appears here. And it oscillates at frequency lambda k. And so I posit some size for the intermittent pressure pi qk in L3 halves. And the reason I posit a size in L3 halves is because pressure scales like velocity squared, and I'm measuring velocity in L3. So I should measure pressure in L3 halves. And I also posit an L infinity norm for this thing. All right, so what do the rest of my inductive bounds look like? I have to tell you how big the rest of these functions are. And I'm going to do so by comparing them all to this intermittent pressure pi. So let's ignore all of the derivatives which appear in this expression for the moment. And let's just say that n and m are equal to 0. So if I look at one of these error terms r, you can ignore the indices which are decorating it at the moment. What this estimate says is that pointwise, r is just less than pi. And that makes sense somehow because r and pi are both appearing inside of the same divergence. So I expect some type of comparability between them. And my assumption is that pi is bigger. Now, what happens when I start taking derivatives? So if I take a spatial derivative, d to the n, what this estimate says is that I can bound the size of that by simply multiplying pi by the frequency that it's oscillating at. All right, so this is saying that spatial derivatives can be bounded by simply multiplicative powers of frequency. All right, so this pi has to be a fairly specially constructed carefully constructed function, because I'm actually positing that derivatives on pi itself are bounded by multiplicative powers of frequency times pi. And I also use some expression involving the pi's to control the material derivatives. So you can think of the scaling here as lambda q is frequency. That's where the gradient comes from. Pi to the 1/2 is like the square root of pressure. So that scales like velocity. And then I have this decoration, which you can ignore for the moment. All right, so these are what my inductive bounds look like. And the final component of the induction is a scaling law for these different pressures. And what does the scaling law say? It says that if I take a pressure which is oscillating at frequency lambda k, so this is pi qk, and I mollify it at a spatial scale which is broader than lambda k inverse, then what happens is I recover exactly one of my old pressures, precisely the one which oscillates at the frequency that I'm mollifying at, times a multiplicative rescaling factor. All right, so
It's not exactly equal.
it's not exactly equal. You're right. Up to negligible errors, basically. All right, so this is the basic setup of the induction. There's, of course, three main ingredients. There's the relaxed equations, which you can think of as a partial wavelet decomposition. There's the inductive bounds, all of which are phrased in terms of the pressure, the intermittent pressure. And there's this scaling law for the different pressures. All right, so how much time do I have?
Yeah,
5 minutes? 7 minutes, okay. Very good. All right. So let me focus on perhaps how we propagate this sort of disjoint space-time support between different terms in my series. All right, so what's the concept behind progressing from one stage to the next in my iteration? It's I take my inductive setup at stage Q, and I define a velocity increment, which is the difference between velocity at stage Q and velocity at stage Q plus 1. And I plug that increment into the equation, and I try and close the induction at the next step. And the increment has some specific form, which looks a bit complicated, but the basic idea is that notice that this nonlinearity is quadratic in U, and I'm trying to get rid of some of these error terms on the right-hand side. So my ansatz for the velocity perturbation is to take the square root, morally speaking, of this error term so that it scales like a velocity. And when I take velocity squared, or velocity tensor itself, I can hopefully get rid of some of these error terms. And I also multiply this measurement of the error by something which is high frequency and has smeared out frequencies. So the width of the smearing of the frequencies is this lambda q plus 1 rq plus 1 up to lambda q plus 1, analogous to this picture here. And I do something similar in order to help myself get rid of the phi's that are appearing on the right-hand side of the relaxed local energy inequality. All right, so what should this velocity perturbation look like? So let me skip ahead a little bit. I guess I also overestimated how much time I had. But let's just look at a picture. Okay, so my velocity increment consists of some high frequency perturbations in my fluid. And if I put a high frequency eddy or vortex in the fluid, what does it do? it follows the coarse-grained flow for a little while until I lose control on that transport equation, and the vortice degenerates into tendrils that disappear. So what I'm doing in this picture here is I'm partitioning space and time into different sets. So every one of these curvy boxes is a different set. And on each one of these sets, I'm going to throw in a collection of high-frequency perturbations, so some kind of eddy, and I'm going to let it move for a little while with the coarse-grained flow, at which point I'm going to turn it off and start my story again with a new eddy. All right, and I need to propagate spatial support information on these eddies interacting with each other, as well as with old generations of eddies. And in order to do so, I have to tell you what exactly this high frequency thing looks like. So what it looks like in our setting is a multi-scale intermittent shear flow. So what do I mean by that? I take a low frequency smooth compactly supported function and I periodize it, and I get these blue circles here. And then I take a high frequency compactly supported function, and I periodize it like so. And I let these little high frequency blobs live inside the lower frequency blue blobs. And in terms of the velocity, what's being depicted in this picture, so this is the support, let's say, in the x1 and x2 variables, and the velocity is facing into the screen. So this is shear flow, which depends on the x1 and x2 variables and the velocity points in the E3 direction. All right, so where does intermittency come in? Intermittency comes in because I've left myself a lot of empty space in between successive oscillations. So if I want to prevent one of these eddies from interacting with some other eddy, I can use all this empty space in between the oscillations to move the eddy around and try and dodge the other eddies. And so that's what I'm depicting in this picture. So because of the sparsity that's built into these objects, I have flexibility in the support. So I can move the support around in some fashion, which will be advantageous for propagating the spatial support properties that I want. And then the sort of picture that you get of your fluid is a collection of these intermittent pipe bundles, which exist at a multitude of scales and frequencies. So I have some very old bundles which are pretty thick, and then I have slightly old bundles and current generation of bundles. And I choose the supports of all these objects so that they're disjoint, which is the inductive assumption that I wanted on some of the terms in this series. All right, so that's all I wanted to say, or all I have time to say about the construction. But let me just say a little bit about what I think some interesting open problems are. So of course, there's the dream theorem, which is to construct a solution of suitable Navier-Stokes solutions, which converge to one of these dissipative Euler solutions. Now, at the moment, this looks rather difficult. So I think a decent partial progress would be to simply raise the regularity exponent compared to the current best construction. So the current best construction is only able to achieve h beta for beta very small. And so it'd be good to improve this exponent beta. I think another interesting problem would be to construct wild solutions to 2D Euler with Lebesgue integrable vorticity at each time, preferably for p as large as possible. At the moment, this has not been done by convex integration techniques, but rather by a totally different method that we'll hear about tomorrow from Misha. And I think one more interesting problem would be to construct solutions to 3D Euler for which the helicity is well defined. And the helicity is a function of time, which is computed as this integral. And in order for that integral to be well defined, it suffices to have u and h1/2. And the exponent that we were able to achieve with Tristan, Nader, and Vlad was just below this h1/2 threshold. So I think maybe with a bit of cleverness, maybe it's possible to surmount that little gap and build solutions with well-defined helicity. All right, so let me stop there and say thank you, Alexis, and happy birthday.